All right, here we go for lesson 3.6, which is GSF Day 2, Graphing Sinusoidal Functions Day 2. And I'm hoping that quite a bit of this will be review, not only of last year's stuff, but when you combine what we know about the basic trig graphs and transformations, that today should be okay. So we're starting the 3-minute review off with graphing the new ones from last class. And if you don't want to hear me go through the details again, then fast forward, just check your graphs, look them up in your notes, whatever. But here we go. I'm going to go through these. For tan x, we know it starts at 0, or at least I remember that it starts at 0. And I also know that there's asymptotes. Asymptotes start at pi over 2 and then skip 1 because I know there's another 0 there. Every other time along the x-axis, there's a 0 or an asymptote every pi over 2, every 3 ticks. And so this one wants us to go all the way to negative pi, but that's no big trouble. And I know it's got this sort of swoop shape. Put a little more detail to it because I know at pi over 4, which is a tick and a half here, it's at 1, right? And I can do that for each of these. However, like my scale along the y-axis will change just to suit my my mood or whatever. But usually along the x-axis, I'll have important points every 3 ticks, which is pi over 2. Okay, and so the tan function then is going to look like this. Try and do this nice and smooth so it doesn't look goofy. That one looks goofy. It's supposed to be nice and smooth, nice and smooth. Yeah, not bad, not bad. Another one at 1 there. Good. Y equals tan x. I'm going to come back to this graph when I have to do cotan. And remember, we graphed the reciprocal functions by graphing their reciprocals, right? We graphed sort of cos first, and then that allowed me to graph secant. And probably it's hard for you to remember what this looks like without graphing that, and I'm good with that. Whether you actually graph the whole thing in, this graph here would be cos x. Put it in dotted so it doesn't distract us as much, or maybe the dots are distracting, I don't know. Nice smooth curve. That's y equals cos x. And then I use my knowledge about the reciprocal function to draw secant. I know everywhere there's a 0. I have an asymptote, 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 shared point, shared point, shared point. And again, the reason for that is ones and negative ones, when you take the reciprocal, they still stay ones and negative ones. That's why the reciprocal and its original graph share that point. Then I fill in the details, and this red graph is y equals sec x. All right, in green, I'm going to draw the cotangent on the same graph as the tangent because they're reciprocals, right? So here I'm going to draw the reciprocal of this one. Remember, where one has a 0, the other one has a tangent, or sorry, not a tangent, an asymptote. Where one has an asymptote, the other one has a 0, asymptote 0, asymptote 0, asymptote 0, and so on. And remember, ones and negative ones are shared points, so shared point, shared point, shared point, shared point. Is anyone listening to me, or did you fast forward? Maybe you're listening. I don't know. Smooth, smooth, smooth. And cotan is always decreasing, and tangent is always increasing. Interesting property there. So there's y equals cotan x. And finally, if you're still with me, the sine, reciprocal of sine, right? is cosecant, and we'll draw the sine function real quick. Right, important points every 3 ticks, every pi over 2. We're kind of smashing into the other one here, but we get sine function. There she is, and she's beautiful. And then the cosecant is its reciprocal, and I think about things like asymptotes, 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 and shared points. Shared point, shared point, shared point, fill in the details. And again, remember the details are things like both a function and its reciprocal are the same sign. So when one's negative, the other one's negative. When one's increasing, the other one's decreasing. When one's near 0, the other one's away from 0. And those are all the details. Dandy. There is y equals cosecant x. Done. Now, we're going to actually start class today with an activity based on these graphs. And so you should know them, because otherwise you're going to look like this. Maybe a little bit more scared. There, does that look scared? Yeah, a little bit. Okay, good. That's a 3-minute review, maybe a little bit more than a 3-minute review, but you fast forward through some of it. Graphing transformations of trig functions. So this shouldn't be a big whoop, because we know our basic trig graphs and we know transformations. So if we put them together, this should be okay. I'm going to come back to this table after, right? I'm going to approach this one exactly like I would approach any old function, as if it was any of our parent functions from unit 0, right? Or even from unit 1. Any of these parent functions with transformations, if I just use my parent function as the sine function, then what do these things do? Well, let's go through it. Let's go through it bit by bit. This is outside of the rule, so it's a vertical expansion, factor 2. This is kind of in with the, and it's kind of hard to see that, but that's in with the x. If I think of this as the basic function, this 3 is inside with the x. So since it's in with the x, it's opposite that. You'd think it's a horizontal compression. You'd think it was an expansion, but it's a compression, factor 1/3. And finally, opposite that, you'd think minus would be left, but it's right, pi over 2. Okay, so those are those 3 transformations, and I'm going to do that on the next grid. I'm going to graph those things and fill in this grid after. I'll fill in this table and this after. All right, so I'm going to approach this in a just like I would have if it was a unit 0, pretending that we spent some time on trig functions in unit 0, and we did a little bit, but not much. Important points every 3 ticks here. This is kind of the scale that we're used to. I know that for the vertical scale, since it's been stretched, I got to be careful that I need to get up to 2. Whoops, going the wrong way. An amplitude of 2. So I gotta be careful of my scale this way. I'm going to go up like this. Okay. And so I'm going to graph, and I'm not actually going to graph it. I'm just going to put little dots or ticks for my first graph. Little dots or ticks for my first graph. And there's my sine graph. Okay, so this original one, I'm going to try and go very light, because this is going to get really confusing. Okay, this is y equals sine x. It's not going to get confusing. Rather, it's going to get. I'm going to blow it up a little bit here. It's going to get cluttered. It's going to get cluttered. So the first transformation was a vertical expansion factor 2. So it means all the vertical distances, all these vertical distances get doubled. So this vertical distance was 0 and it stays 0. Where it was 1, it gets doubled to 2. And notice I'm just doing my important points here. It was 0, it stays 0. It was 1, and it expands twice as far to -2, and so on. And so here's my next graph. I'm going to try and do a good job of this. And you can see with a couple more transformations, this is going to get pretty cluttered. So this graph here, this green graph, is what, it's not the final yet, right? All we did was the vertical stretch. And that changed something about the trig function, right? It changed the range, and it also changed one of these words, and we'll talk about that later. Notice we want to do our stretches and squishes first, so that's why I'm leaving the right pi over 2 for later. Horizontal compression factor 1/3. This is actually a challenging thing to do, and I'll tell you why. It means all of the horizontal distances, all of these horizontal distances get cut in a factor of 1/3. So, you know, this was 0 away, so it stays 0. So we're going to stay with this point. But now, and I'm going to do this for every important point, where it was 3 ticks, you can see that, it gets cut in 1/3. This is one of the reasons why we like this scale. 1/3, it gets cut back to there. So this point gets cut back to there. And this is actually going to be a big hassle. 6 squares, 1, 2, 3, 4, 5, 6 squares, 1/3 of that, well, gets cut back to 2. And maybe you're starting to see a new pattern, but I'm going to continue with this squishing business. Where it was, I think that's 9, because there's important points every 3 ticks, and this is 3 important points out, 1, 2, 3. 1/3 of 9 is 3. So where it was 9, now it's 3. Where it was 12, this point's going to get cut back to 4. Now notice what's happened here. There's my first cycle, right? And then it's going to start repeating itself. Notice, to actually fill it in, because it asked me to graph this graph from x, goes from 0 to 2 pi, right? I'm pretty sure it asked me for that. Yeah, to 2 pi. Right now, I'm nowhere near 2 pi. So if I actually wanted to do this compression thing, I'd have to have more of this green graph that I can squish back. Now luckily I can kind of see a new pattern where it looks like the important points are occurring not every 3 ticks anymore, but every tick horizontally. So every tick, important point. And I can sort of follow that new pattern, every tick, important point, where I just go middle, high, middle, low, middle, high, middle, low, important points. Not every 3 ticks, but every tick. Okay? And so here, important points were every pi over 2 or 3 ticks. It's not like that because I've compressed it by a factor of 1/3, every 1 tick. And that is actually divided by 3. That's pi over 6. Every tick, or every pi over 6, I've got an important point. Phew! Okay. It's got to be an easier way to do this, or think of this, because what a mess I'm making here. Okay, so this blue graph is y equals 2 sine 3x, and it's still not done yet, because I still got my, oops, wrong way. I still got my final graph to do, my final transformation, which is moving right pi over 2. Well, how much is pi over 2? Pi over 2 is actually that distance. It's actually 3 ticks. So I'm going to write that in there so I can remember that's 3 ticks. When I set up the same scale, that's 3 ticks. So I'm going to move this blue graph over 3 ticks. Each point, move 3 ticks. 1, 2, 3. This point, 1, 2, 3. Phew, I'm going to get confused about where all my ticks are. 1, 2, 3. 1, 2, 3. Oh, hang on. What I could have done if I was smart is just move this over 3 and then started my pattern. Middle, high, middle, low, middle, high, middle, low, important points every 1 tick, and I don't need to move every single point over 3. I can just follow the pattern. Middle, high, middle, low, middle, high, middle, low. And it does turn out that I've moved this point over 3 ticks, 1, 2, 3, but I haven't thought of it that way because it's taking me forever to move every point over 3 ticks. Why don't I just move the starting point over and then follow the new pattern? Low, middle, high, middle, and then I'll fill it in from 0 to 2 pi. And notice right now there's a little gap here with no purple graph, so I can go backwards. High, middle, low, middle, high, and then I've filled in the graph for all of 0 to 2 pi. This graph right here now is my final answer. And it feels like, because what we know about trig functions, and there's a lot of patterns going on here, that there must be an easier way to do this. And that's what we're going to pick up in the second part of the video.